So that's kind of the overview of numerical. So let's actually do an example here. All right, so this example, what we're looking at here is called a current lead. All right, a current lead is a wire. It's a fancy name for a wire. And in this problem, what we're trying to do is take current from room temperature, 300 degrees Kelvin, down to cryogenic temperatures, say 40 degrees Kelvin. So why would anybody want to do this? Well, if you can get it down to these temperatures, you might be able to get that current into a superconductor. If you're in a superconductor, then there's no resistance, and so you might have certain applications where that is really important. So to get the current into this, say, superconducting magnet or whatever, you have to get it down to these temperatures, and there's resistance as you do that. So like we're looking here, see my little pointer again. Right, so here we're saying there's 1,000 amps going through this little wire. That's a lot of current. So you can bet that there's going to be energy generation inside this wire. There's going to be a heat generation due to the resistivity. And if you look here, where we say there's an electrical resistivity, rho E, equal to that number of ohm meters. Okay, so we know that as the current's passing through, it's generating, there's thermal energy generation inside the domain. So what else are we told? We're told that there's a contact resistance. So maybe like the wire up here is, soldered or something. And then down here, there's another contact resistance. So we have two contact resistances. The wire's length is 20 centimeters. The diameter is 0.7. And we're given the temperature. So what we want to do in this problem is come up with a model of temperature as a function of position along the wire. Okay, we're going to assume for this, eventually we could prove it, but we're going to assume now that this is a 1D problem, and it's a 1D in the direction along the axis. We're going to neglect any temperature profile in the radial direction. Okay, so let's go through our steps, right? The first thing was we have to, step one was define our many nodes, right? Define however many nodes we have. So step one, define n nodes. All right, so I've drawn a picture here just to, you can kind of sketch it if you want to, but what are we doing? So we have our domain. Our domain starts here and ends here. Then we have our coordinate system X, right? We define that coordinate system X. We want to position some nodes along this domain, and the nodes are the locations where we're going to solve our algebraic equations. Okay, so we first want a node right at the boundary. Why do we want a node right at the boundary? Well, because eventually we're going to enforce boundary conditions. And it's a lot easier to enforce a boundary condition when the node's at the boundary than if it's offset from the boundary. Okay, so we're going to start with a node at the boundary here, and we're going to have a node at the boundary here. And then we are going to space them in any way we want, but in this example, we'll just do it evenly throughout the domain. Okay. By the way, evenly throughout the domain is probably the worst possible way to do it. And why is that? Well, because really you want the most nodes where say most of the action is, right? Where the biggest temperature gradients are, you want the most nodes. So if you're just interspersing them kind of evenly throughout the domain, then you're pretty much guaranteed that you're wasting nodes at some point. But for our purposes, of course, it's just easier to understand it this way. So we'll start this way. There's tools out there that do this kind of thing automatically for you. If you set it up the right way and space the nodes for you. But to understand it, we'll kind of start this way. Okay, so step one, define n nodes. And then we're going to write some equations for the position of the node. So let's say we want to compute the position of node xi. Right? What is our x position for the ith node? So I'm going to come up with an expression that gives me that position in terms of I. Okay, so that would be what? So it would be I. So here's the expression. I'll explain it. I minus 1 over n minus 1 times L. Okay. So we are taking kind of a fractional position, I over n, but we're subtracting I minus 1 because we want xi to be 0 at I equals 1, right? So starting with I equals 1, we want x equal to be 0. So 1 minus 1 is 0 over n times L, that's 0. Okay, why n minus 1? Well, because we have right? This is kind of our first domain here, second, third, so on. And then to the n-1 is that domain there, right? So we actually only have n-1 segments in the domain, right? Just stare at that if you don't believe me, but it ends up being there's only n-1 divisions in the domain or segments in the domain. Okay, so that's our position xi. And that is for what condition of I? So that's for I is equal to 1 to n, right? For every I that is in that index set, 1, 2, 3, 4, all the way up to n, that equation is true. Okay, so we've defined the position of each node there. We may also want to have available to us the node length, delta x, and that is going to be L over n-1, right? Again, we're taking the total length divided by the number of segments in that domain. Okay, so that's step one. Step two is we're going to do a first law on the control volume around each node. First law on the control volume around nodes I. All right, so let's see. I've drawn down here at the bottom. Right, we've got this domain. So we're picking some node, right, kind of in the middle here. And we've got I-1 and I+1, and we kind of blew it up. So we've drawn our control volume so that it's kind of symmetric or evenly distributed around I. This is not the only way to do it. You could set it up where the control volume actually goes right through I and maybe through I-1. There's different ways of doing it. This is just sort of the default, the best way to do it. And we'll proceed this way, but just keep in mind you can formulate it some other ways. Okay, so we draw it this way. What are some things to note? So this length here, right? This is delta x, right? And delta x, and so this length here is also delta x. Right, so delta x is both the separation between the nodes, but also the length of each domain. Right? That's probably obvious. Okay, so we have here now a couple of things going on, right? We have from the top, we have heat flow going from I-1 to I. Okay, so we draw an arrow Q dot top, I-1 to I. And then from the bottom, we have the same thing, right? I+1 to I going this way. And in this problem, we also probably have generation going on, right? Or we do have generation going on. So another thing is, why are we drawing all the arrows going in? I mean, you could draw where Q dot top is going I-1 to I, Q dot bottom is going I to I+1, so it would be reversed. Well, the reason why we do it this way is because actually we don't know which way we don't know which way heat's flowing necessarily when we're setting up this model. So if we don't actually know and we don't have any real reason to believe any which way, why not just draw everything going in so that it's easy from a modeling perspective to always model every single node the same way. If we model every single node the same way and everything's going in, then all our conventions are kind of neat and tidy and we can duplicate the equations and it just makes our lives easier. Okay, so we're just, by convention, we're just going to say everything's going in. Okay. Okay, so our first law ends up being, we've drawn everything going in, so it's in plus generated equals out plus stored, so we just have Q dot top plus Q dot bottom plus G dot is equal to 0, right? And in fact, we might want to say Q dot top I, Q dot bottom I, G dot I equals 0, because this is for this specific node. Okay. All right, so step 3, so far it's kind of like pretty obvious. So then step 3, we just need to come up with rate equations now. And so step 3 was rate equations. Okay, so we need an equation for Q dot top, Q dot bottom, and G dot in order to solve this. And remember, now we're not doing this for a differential control volume, right? We're not saying Q dot R plus dr, doing the expansion, all that. We're using algebraic approximations, right? And that can be done using the resistance model. So let's come up with, let's start with, say, Q dot bottom. Okay, so Q dot bottom, I. So what's an equation that gives us heat transfer due to conduction between two conducting positions, or conduction between two positions for this? Okay, so it would be, let's see. Yeah, so Q dot bottom is going to be T I plus 1 minus Ti divided by R conduction, right? Again, pay attention to the direction I drew. So I plus 1 to I, that's the same direction we drew the arrow. So we are assuming that Q dot's positive from I plus 1 to I. So we write the temperatures in that order, okay? And then what is this resistance here? Well, the resistance is just, that's going to be the distance that we have to travel, which is delta X divided by conductivity K times the cross-sectional area available for heat flow. Okay, so that's going to be, in this instance, it's, if we just write it out and substitute in R, it ends up being K AC times Ti minus 1, I'm sorry, I plus 1 minus Ti divided by delta X. Delta X is our distance that we have to conduct. Okay, so that's for the bottom. So now we actually have an algebraic equation, right? This is a simple, it's this simple. We have an algebraic equation in terms of our temperatures, Ti plus 1, for one of the heat terms. Okay, so we do the same thing again for the top. Q dot top I is equal to, let's see, Q dot top I. Now this is going to be Ti minus 1 minus Ti over R, and that gives us, again, K AC, Ti minus 1 minus Ti over delta X. Okay. What's the last thing? So we have generation as well going on here. Kind of running out of room. Just right up here. So our generation term, right? This has to be our volumetric generation times the volume of the node that we have. Okay, and in this case, because it's resistivity due to electricity flow, it ends up being rho E times delta X over AC. That's just kind of the G dot triple prime, the generation part of it due to electricity flow times the current squared. Okay, so this thing gives us, for this node, the generation that's occurring in watts. Okay, eventually now we want to combine all this stuff together. So we take, let's see, we take this piece, and this piece, and plug them all in here, right? And now we've got a system of equations that are just in terms of temperature. Right? So we just see temperature and a bunch of constant stuff, right? So now we have an algebraic equation for node I, right? You do this now, again, you can do this or repeat this process for every node, but we have to be a little bit careful, right? We can't do this process for the end nodes because the end nodes are a little bit different. But the end nodes are not interacting in the same way as a middle node with its adjacent nodes, okay? So we're gonna say that this is valid, right? So this equation here, this is valid for I in what range of I's? It's gonna be from node 2 to node n minus 1, right? So now we've got n minus 2 equations. Right? We do this for every single node I. We have n minus 2 equations. We need 2 more equations in order to solve this. Okay, so that brings us to the boundary conditions. All right, so our boundary conditions, again, what we're going to do, we're just kind of repeat the same process. So we go back to our second step? What do we say for second step? We've already defined the nodes. The second step is first law on the control volume. So step 2 again is we're going to do first law on the control volume. So first law on, let's take this one here, node 1 to begin with. So here we have Q dot top plus Q dot bottom, plus the generation is equal to 0, and that's for node 1. All right, a couple things to be careful of here. We have this distance here. This distance is delta X. So the control volume is no longer delta x long, right? It's actually just delta x over 2 long. So when we're talking about generation in this domain or anything that has to do with like the volume of the domain, we only can think about that half of the domain that it's actually using, right? We don't do anything like draw this up into the base material or anything. The domain stops at the end of the node where we position it. So the boundary nodes are only half wide. Okay. Okay, so we did let's come up with some rate equations here. So then q dot bottom is the same thing. Q dot bottom is just going to be now T2 minus T1 over R, which is delta X over K AC. It's the same thing, it's just for T2 and T1. T2 and T1. Q dot top. Right, so Q dot top is maybe now a little bit different. So now we have to write an equation in terms of what's happening at the top interface. And what's happening at the top interface, because we look back, but it's contact resistance. Okay, so we can still write a resistance-based equation for this, but let's do it for what's happening at that boundary, and that is contact resistance. Okay, so then Q dot top, let's see, where am I in my notes here? So Q dot top, so that's going to be, let's see, TH, right, the temperature of the material outside minus T1, that's our driving temperature difference. And then we divide by the contact resistance, which is R double prime C, that divided by A, so A goes up in the numerator, right? So that's our equation for the top, for node 1. This is for bottom node 1, top node 1. Right, so you can see how this process kind of works. You go through, you're just drawing control volume, you do the rate equations, and you just keep going through this process. So the last thing here was G dot. So G dot for 1 is going to be the same formula as before, except again, we can only use half of the domain. So we have rho E times delta X over AC times I squared. But the difference rate is we only are using delta X over 2 here. So we have to actually divide everything by 2. And so it's rho E delta X over 2 AC times I squared. And so now we've accounted for generation being only half of the volume. Yeah.
If you didn't have contact resistance, could you say node 1 is at pH?
Yes. Yeah, very good question. So this specific example, like let's say we had some, again, like network of resistances that get us between some known temperature and our temperature at node 1. In this case, it's just a single contact resistance. But if it was a complex system, you could model that whole resistance network, have that be the rate equation for Q dot top. If it's a temperature, like you're saying, the equation becomes as simple as T1 equals TH. And that is your equation. Yeah.
I'm a little confused by the halving of the delta X for the top nodes.
Okay, so yeah, the generation rate equation, this is for a condition where we have electrical current flowing through, and then we have to convert current and resistivity to generation. And so the way that particular equation works is you're looking at the length that the electricity has to flow, which is delta X. And that's part of the equation. So here, the length of electricity has to flow across this domain, and from here to here to generate electricity. That's to generate heat. That's only delta X over 2. If you had another situation, let's say we were given G dot triple prime as a constant, then it would be G dot triple prime times V, and V would just be, right, it would be delta X over 2 times AC. So it's the same kind of idea. You just have to scale it down by the actual volume of the control volume that you're using. Okay, any other questions? Okay, so anyways, we go through this process. We now have another equation, right? So we get rid of this. So we now have another equation here, right? This, and this all have to add up to be 0, according to our step 2 energy balance. And that's another equation, right? So now we have n-1 equation. So we do the same thing then for the bottom. It will spare you the details on that, but it's exactly the same process. We have a contact resistance. Instead of 1, we're using N, and instead of TH, we're using TC. And it's on the bottom instead of top, but it's basically exactly the same process. Okay, we end up with now, with this one over here too, now we have N equations and N unknowns, and we can just plug it into E's and solve it.